In a previous video it was described the construction of an X-ray spectrometer for use in X-ray fluorescence experiments. In the video that you are now starting to watch are shown the results of some X-ray fluorescence experiments with different materials, including some minerals. First of all, it should be noted that these results cannot be compared with those of commercial XRF equipment, but this does not rule out that the device could be useful, especially for detecting elements of medium or high atomic number. Please, keep in mind that the construction of the spectrometer and the XRF experiments shown here should be considered as a retirement hobby. The spectrometer detects individual X-ray photons using PIN photodiodes. One of these, the BPW34, which have a surface area of 7.5 square millimeters, is inexpensive and works fine. Because the surface area is small, obtaining a reasonable spectrum with a single BPW34 requires about 10 minutes or more depending on the size of the sample. It should be noted that, often, a couple of minutes is enough to see a well-defined signal and identify the element. To reduce this time in half, the surface area has been doubled by using two BPW34 photodiodes in parallel. Tests have also been made with a much larger photodiode, the Hamamatsu S3590-08, with a surface area of 100 square millimeters, and a cost about 100 times higher than the BPW34. Since as the size of the photodiode increases so does its capacity and the signals produced by the X-rays are weaker. With bigger photodiodes a reasonable resolution can only be obtained if cooled to reduce noise. With 1 or 2 BPW34 photodiodes it is sufficient to cool below 5 degrees Celsius, while with the Hamamatsu 1 it must be cooled to about -15 degrees Celsius. The X-ray source is a crown with 6 capsules of americium-241 of the type used in some smoke detectors. They have been glued to aluminum cylinders cut at 45 degrees so that the radiation is focused in the center and just above the crown. Some aluminum parts have been machined to place small samples when necessary. Americium-241 emits X-ray photons of various energies. The predominant ones are those of 59.5 kV, although the photodiode detect them with much lower efficiency than the others of lower energy, which are emitted in the range of 10 to 25 kV. With the energies involved, below 60 keV, a X-ray photon that reaches the sample can cause two processes. The first is the photoelectric effect, where the photon kicks an electron. If the electron that is expelled is from the innermost level, immediately, the electrons from the upper layers will fill the gap and in the transition, X-ray fluorescence photons will be emitted. If the electron that fills the gap comes from the level immediately above, the line of the X-ray spectrum is called Ka. If the electron comes from the next layer, the line is Kb. If the electron that is expelled is not from the lowest level but from the level immediately above, something similar happens. In this case the lines are called La and Lb. Since the energy of the photons emitted in fluorescence is equal to the energy difference between the levels, its measurement tells us which chemical elements are present in the sample. The energy of the X-ray photons emitted in the fluorescence must be lower than that of the X-rays used to excite it. If an americium-241 X-ray source is used, which emits photons with a maximum energy of 59.5 kV, only the Ka line of elements with atomic numbers up to approximately 70, ytterbium, can be observed. Elements with atomic numbers greater than 70, such as tantalum, tungsten, gold, mercury, lead, or bismuth, can be detected from their L lines, but their K lines cannot be observed. In elements between approximately cerium, atomic number 58, and ytterbium, atomic number 70, both the K lines and the L lines can be observed. The photoelectric effect is the predominant interaction between X-rays and atoms of low atomic numbers. As the atomic number increases, the photoelectric effect decreases and a second phenomenon called Compton effect appears. The photons behave like particles that collide with the electrons of the atoms as if they were billiard balls and transfer energy to them. The result is that the sample deflects X-ray photons, which come out with a lower energy than they had before the collision. These photons give rise to signals that can be confused with fluorescence lines of some chemical element. In the XRF spectrum of silver, atomic number 47, the signal due to the emission of the Ka line at 22.2 kV is observed very intensely. However, in that of barium, atomic number 56, in addition to the Ka and Kb lines, at 32.2 and 36.4 kV, many lines with lower energy are observed that do not correspond to possible impurities but are due to the Compton effect. With elements of higher atomic number, the entire repertoire is observed, the Ka and Kb lines, the L lines and in between other lines, rather bands, due to the Compton effect. Since the lines in an X-ray spectrum that allow us to find out which chemical elements are present are those due to the photoelectric effect, they are detected increasingly weaker when the Compton effect is in action. For this reason, the detection of elements with atomic numbers higher, approximately, than tin, atomic number 50, requires an acquisition of the spectra proportionally longer to compensate for the lower efficiency in the detection. If we consider the detection of low atomic number elements, we must take into account the attenuation that occurs in the path of the X-rays inside the spectrometer, first in the window through which they enter the X-rays and, then, in the material that covers the silicon in the photodiode. Since the photodiode must be absolutely dark, it is necessary for the X-rays to reach the detector through an opaque window, but the material of the window causes attenuation of the X-rays. The attenuation in a given thickness of a material depends on the type of material and the energy of the X-ray photons. It increases greatly when the energy of the X-rays decreases or when the atomic number of the material increases. From the values of the attenuation coefficients found in the tables, it has been calculated that if the window is a whole covered with aluminum foil, even if the aluminum is very thin, kitchen aluminum foil is about 0.05 mm thick, the attenuation it causes is very large, below 10 keV. If low-energy X-rays are to pass through, the most suitable material is beryllium, so in the spectrometer that I have built the window is a piece of beryllium foil 0.15 mm thick taken from an unusable proportional counter. In commercial XRF devices, the beryllium window is much thinner. After the window, the X-rays must pass through the transparent plastic cover of the photodiode, which in the case of the BPW34 is 0.7 mm thick. If we assume that it is a plastic with a behavior similar to polystyrene, the attenuation it causes is 50% for the 6 kV photons. At 4 kV the attenuation is practically complete. For this reason, in my spectrometer the first element that can be detected, and not very well, is manganese, atomic number 25. Chromium, just before it in the periodic table, is not detected. From manganese onwards, the elements are detected better and better until the detection efficiency decreases due to the Compton effect. This means that when there are signals from more than one element, the intensity of the signals cannot be directly translated into the proportion of the elements in the sample. The resolution of X-ray fluorescence signals depends on the electrical noise, but fortunately, the noise can be greatly reduced by lowering the temperature. In the circuit I described in the video before this one, with a single BPW34 photodiode as a detector, it is enough to cool it below 5 degrees Celsius to reduce the noise enough to have a good resolution. In practice, there is only good resolution at room temperature if very small photodiodes are used. With a large photodiode, such as the Hamamatsu S3590-08, you have to cool up to about -15 degrees Celsius to have an acceptable resolution. With 1 or 2 BPW34 photodiodes, the resolution is good when cooled below 5 degrees. This temperature can be easily achieved by placing the detector inside an expanded polystyrene box with ice packs and drinks cans taken from a freezer. After half an hour the temperature has already dropped below 5 degrees and spectra can be taken over more than 10 hours, without the need to add more ice. An important parameter of the spectrometer is the resolution, which is defined as the width of the signals at half height. The value is approximately between 2 and 3 times the standard deviation of the noise. It is not the same for all signals, but there is not a large variation. In the case of my experiments with BPW34 photodiodes, the resolution of the americium signals varies from 1.5 kV in the lowest energy signal from americium 241, to 2 kV in the highest energy signal. A resolution of 1.5 keV implies that, in the low energy region, signals with an energy difference greater than this value can be seen separated, such as the lines La and Lb of lead, at 10.5 and 12.6 kV. On the other hand, the L lines of tantalum, at 8.1 and 9.3 kV, will not be seen well separated. Improving resolution means reducing noise with an improvement in the circuit design which, as a simple hobbyist, is beyond my reach. Regarding the separation of the signals corresponding to consecutive elements, it can be seen that the signals of the elements with low atomic numbers, as Mn to Zn, are tightened, whereas those of the elements in the middle of the table, such as Ag to Ba, are a bit more widely spaced. And the signals are even more widely spaced in the rare earth elements. This is easily understood from Moseley's law, which states that the energy of the photons, Ka lines, is not proportional to the atomic number but to the atomic number raised to the square. This spectrometer is not very useful in the low energy region, where the resolution is not good enough to differentiate the nearby elements. Here, scintillator or proportional counters can have more resolution, however, as the atomic number increases, the use of photodiode detectors is much more interesting. If you've made it this far, I can only hope that the XRF spectrometer I've described will encourage you to build others that work much better. If so, please, share your results.